Okay, so first thing, just to clarify, I definitely rearranged the GitHub repository, renamed some files, made some things, some of the projects a little more clear, matched the names to the videos. Um, so be sure and get latest there. Um, the other big thing that I added is cheat sheet. So this is a little something that I started working on, and I think it kind of puts a lot of the core information you need in one place. And so that is here. So right at the top is different variables or registers. We talked about those last time, and this time we're focused more on the names. The numbers are there. That's a cross-reference. There's going to be some disassembled source code and some other times when it's nice to see the number value. But really, we're going to be operating on the names of the registers. Um, Later on, I'm going to cover the delay slot a little bit more. You can kind of take a peek here. And then down below, I included some instructions and kind of how they break down. I'm still figuring out the tables, but overall, I'm really pleased with this. By the end of this video, we will have covered at least 10 MIPS instructions, and we're able to draw on the screen. So um, that's pretty impressive. Very powerful instructions and not overly complicated, in my opinion. But we'll see some more of those today, and mostly covering the first branching instructions, and I think we'll need the LA instruction as well. All right. So as the series progresses, we'll be adding more instructions to this lower list, and any other tidbits that you need for development will also be added to this file. Just to give you a single starting point. Okay, so today we're kind of just going to go right to some code. So the goal for this video is to draw a line. It's pretty simple, but it's going to be a really nice way to start using some of these other instructions. With that being said, we started with a copy of our video 4 source code. Has our init routine at the top here. Oops. Our video initialization is here, and then our eternity loop is still here. We're gonna, because it doesn't matter in our case, we're gonna be writing our line code here. Draw a line, and we're gonna start with horizontal. And depending on time, we'll move on to a vertical line, and we'll probably do a second video or a little break tonight, and we'll do a square or a rectangle. Okay, so here I have my command line, and I can just always run make, and this is just runs my batch file. Nothing's really changed here. So we can see I've got a make.cmd, I've got a header, I've got my source code, and it generates my output file. Okay. So that being said, we've got a couple of things that we're going to change. The first thing is up here we have our VI origin, which is the starting address for our frame buffer. If you recall from the last video, we used this range, and what it does is it actually looks at our source code and treats it as though it's a color. I don't know if you would call it casting, or it was really kind of just the easiest way to get something on the screen. But we need to change that. So, just so that we kind of know where that memory is going to be, because we only have 4 or 8 megabytes to really play with. So, really, I'd just like to put the put our frame buffer in. So our code by the bootloader is copied into from the 0 to the 1 megabyte range of RAM, and then it's executed from RAM there. So we don't have anywhere near a megabyte of RAM or of code, but just to steer very clear of that, I'm going to have the frame buffer start from the megabyte 1 mark, basically, which means that I just have to change. Whoops. So in the calculator, I was talking as I did it, but basically I just did 1024 times 1024, which is 1 megabyte. We all know it's just a smidge over there, like that. But here's the hex representation, so it's a nice even number. And so we come here and we do that. And now our frame buffer is looking at a blank unused portion of RAM. So that is where we are going to draw our line. And just to point out again really quickly, we are looking at 320 by 240 and 16-bit color. So that being said, let's come up here, and just to show you, it's already in our lib folder, is the colors 16 include. And so I'm going to just grab this line, 16 include. So also in this folder, there's the approximate colors PNG, and this is so here. Let's look at this. Basically, this is a whole bunch of constants, and to give you some nice names to go with the colors. And so here's the actual color value over on the right, and so we can type red 16, and that is the 16-bit red. Just makes it a little bit easier to do things, and with the 16, or as we can see in this file, the 32, we can use, you could actually switch color depths, like between levels and cutscenes, or however you want to approach it. But both of these files are already created and should be helpful. In addition, there is this file. Wow, I guess Paint will open this. So this, basically I took the original values from an HTML site and I gave them credit down here at the bottom. This is the link and where I got these values, and so these are the approximate colors. On the N64, they may not be anywhere close, but they're going to be somewhat close. So that being said, let's draw a line, and I'm going to go with lawn green just because I can. So we'll come back here, video 5, here. So we got a couple of things going on here. We're doing 16-bit colors, but N64 really operates on 32-bit values so much better. More efficiently, it's just better all the way around. So what we're going to do is, let's see, I'm going to say LUI T0. Again, we're just operating in our temporary registers. And lawn, oops, how did I spell it? Oh, and they are kind of grouped by their color types here. So we can go down to the greens, green colors, lawn green 16. So we're going to just grab that, paste that, and then we're going to do ORI, which is just going to load the same thing into the lower half of that same register. So now we have 2 pixels of lawn green 16 in our register. And once again, I'm going to come back up here and I'm going to grab this value. And I'm going to use the LA instruction, which is a pseudo instruction. That means that the compiler takes this one instruction and makes it into 2 or more. Sometimes it's just 1, it's just a renaming that's convenient, but in this case it's going to turn it into an LUI and an ORI, but it's just kind of a little nicer way to write the code. Okay, so we have our 2 pixels. So let's define a little bit more about what our line is going to look like. I think that we should come down 15 rows from the top, and I want to come in 110 rows, or 110 columns, and I'm going to make it 100 pixels long. Okay, so that's our goal, and I'll move this up. Okay. So Striker asks, how does the compiler know what LA is referring to, or is it only used for substituting very specific commands? The BAS compiler has some options. I'm gonna go up. This is a good question. So I'm gonna run with this for a moment. ARM9. There we go. And so this is the source code for the compiler, and I believe it can be done as a external file, and so we can see that here. These are Arch files, which, if you recall, is also the term we use at the top. Arch is our keyword here. N64 CPU. So here we can see the N64 CPU, N64 RDP, RSP, and these are the other platforms that are supported here. So if we come into here, it includes others. So I'm not sure which one it'll be in, but we'll go take a look. So in the MIPS EB folder up here, and I'll just kind of come in here, find LA. Okay. Maybe in this one. Oh, sudo. Oh wait, this said sudo at the top. All right, I'm going a little quick here, but there is the LA. So it's kind of a cryptic file format. There's some bits in there. I haven't created this file, but this kind of lets you know that you can create your own instructions from here. just whatever the bit patterns are. Probably have to read quite a bit to understand some of these. So I'm not going to go any deeper than that, but you can do some pretty cool stuff with this. So I will leave it at that. Okay. All right. So our window, back to our line. Our window is 320 pixels wide. To move down 15 rows is basically 320 times 15. And I'm going to calculate that out because in the past I had a really small bug that caught me off guard here. And I am glad that I did that. Okay. In this case, we're good. So 320 by 15 is just brings us down our 15 rows. And then we need to add 110. Okay. But the thing to remember here, and this is where it is, this is our pixel counter, but each pixel is not a single byte. Each pixel is actually 2 bytes because we're in the 16 bit per pixel mode. Right there is where that's defined. So we take all of that and we times it by 2. So that being said, I'm going to take T2. Oops. Had a bug there. T1. Okay, so so what we're doing here is we're going to find the location of our first pixel in our frame buffer, and we're going to assign that to T2. So to start, we're going to use the, we've actually, T1 is our start. So we're going to do add I, T1, T1, and I'm going to do this. So and I've mentioned it before, but this is, in order to get really good at assembly language programming, you really want to pay attention. You want to know what the compiler is doing for you and where you kind of need to step in. So in this case, I double checked the math, but I didn't finish it because let's see. Here, I'm going to be in decimal mode. 320 times 15 lines is 4,800. Add 110, and then I'm going to multiply by 2. And so what I'm really looking for here is I want to know if this value gets bigger than 16 bits. And so we can see down here, this is the 16-bit representation, and the top 2 leading are zeros, and we've got 1, 2, 3, 4 sets of 4. So we're still in the clear. This is the value that the compiler is going to calculate for us and put into this value. But instead, this really just makes the code clearer in my opinion. And yes, there's a lot of opinions in programming. Okay, so we now have our starting point on the screen. We have our color loaded, and since we're going to do our color, our line for 100 pixels, we know that and we have loaded up 2 pixels of our color. We need to do 50. We need to write the value 50 times. So that's where we're going to get into our loop. Okay. So just like all counting loops and things like that, we have choices that we can make here. One is, do we count the 50, or do we figure out what our ending address is and test against that? In this case, I think I want the ending address. So I am going to add I, and I'm going to put this value into T2, but I'm going to take T1, and I am going to (100 pixels times 2 is actually 200. So now I'm going to start in T1, and I'm going to end when T1 equals T2. Okay. Sorry, kind of thinking ahead here. But we'll see this as we write the code here. So at this point, all of my variables are initialized. So I know, you know what, let's do our first. Let's load up our first 2 pixels. And so we want to do, we're going to use this store word. We're going to store T0, which is our pixel colors, and we're going to put that into T1. And that's it. That line, we just wrote out 2 pixels of green. And this is enough good work. Let's see what it looks like. And debug. Okay. So as I've said, our code actually is located at this 8 3 zeros and the 1 with 3 zeros address. And so I'm going to just let that BIOS code run, and we can get to our code. And here at the bottom we can see this is our loop forever. The 10EC is on its same line, so I am going to set a breakpoint. Set breakpoint at cursor, and I'm going to let it run. And there we can see 2 pixels of green. Well, it looks wider than it does tall, so I'm going to assume that that's our 2 pixels. So we're on the right track. Yeah. Doing good. I'm going to go ahead and get back to the code. All right. So, thing is, we need to do that a few more times. So, we need to now add immediate onto our T1 value. So just to be clear, the first occurrence of T1 here is the destination. The second occurrence means that we're going to use that as part of the calculation. And because we are storing a word, which is 4 bytes, we're going to increment T1 by 4 bytes. And let's see, we're going to say, we're going to do our first branching. So we're going to say B, N, E, T1, and T2. But now where are we going to go? We're going to go back to here. And so we're going to put in a label. And we're going to call this store 2 pixels, and you need the colon at the end of that. And here we're going to say store 2 pixels. And we talked about the delay slots, and we're gonna come back to this. But we're just gonna put in a NOP. NOPs are always safe. Don't even hesitate. Just put in a NOP. Not a big deal. And so we're gonna do that. And one of the ways to kind of think about this code, if you're come from any of the C-based languages, is this is a little bit more like a do while kind of style. So here, in fact, I'm going to do that. And the reason that I say that is because it's always going to execute this loop once, and we do the test at the bottom of the loop and return back to the top. So it just kind of has that more of a do while kind of a style. And so that might actually work. Let's try it out. And again, BP set. There is a trick that we'll start using soon where we don't have to set that breakpoint every time, and I'll show that soon. So I just used the hotkey, which looking here is F9, in order to set that breakpoint, and I'm going to let the code run, and we have a green line. That was the goal, and it's very nicely centered, pretty even left to right, which once again was part of what we were trying to do. If we look here, starting at column 110, because 110 plus 100 plus 110 equals 320, which is the width of our screen. And so that is why that works. Nothing else on the screen, all black. Okay, so next we're going to talk about the so I'm going to go ahead and close that. We've accomplished our goal, but I'm going to come back and talk about this delay slots, because that was what this was about. So I'm going over to my cheat sheet here to kind of show you what I'm going for here. So there is a whole chapter on the MIPS pipeline. It's in this document, and by all means read it, and you may come up with a different interpretation or understanding of this, but you can see the branch delay, load delay, those types of things are all mentioned there. Pipeline interlocks. It can get really technical, so I'm going to give you kind of that mental model that where you can actually use a delay slot. So the N64 has a 5-cycle pipeline. So each of those little pipeline stages does different things, and some instructions need them, some instructions need all of them and more. And so what we can see here, again, this is my example. If you think of the branch and jump instructions as needing 6 cycles of a 5-cycle pipeline, you immediately know, well, there's kind of this wasted 4 cycles. And again, if you look here, you see that the register to register instructions, which include most of what we're writing here, the only thing that so if we look at the instructions as branch and jump instructions, load and store instructions, then register to register instructions. That being said, we can see that LUI is going to fall into the register to register. ORI is going to be register to register. Now, LA is a pseudo instruction, and these are the ones that you do have to be careful of. They do not work in delay slots because, as we said, this is actually two instructions. So what will happen is only one of them will be executed. So you do have to watch the pseudo instructions. But the add-I instructions, again, are register to register. The SW is a load and store instruction, which takes 5 pipeline cycles. And then we have another add-I and our branch instruction. So, this is a little bit of an explanation. I hope it's clear for everybody else, but if you come here and you just take a look, jump plus a register to register takes 10 pipeline and cycles. 10 pipeline cycles, most efficient approach. Highly recommend it. Once again, any hesitation, use a knob. But if you do a jump plus a load and store, officially you shouldn't. If you do, what's going to happen is it's going to take 11 pipeline cycles, aka 3 clock cycles. So once again, you're right back to wasting 4 steps in the pipeline, 4 pipeline cycles. Not ideal, and it will work because the load and store on the N64 is a blocking operation. So if it needs an extra clock cycle, it will use it. For example, on the PlayStation, it is not a blocking instruction, and it will cause you problems. So really don't do it on PlayStation. And if for some reason you get a crazy idea and think you can do a jump and a jump, maybe if you're thinking like a nested if condition or something like that, so it'd probably be more of a branch and branch. It will take 12 pipeline cycles and have some really unpredictable behavior. Because if you think about it, if you put a branch instruction in a delay slot, then what about the second delay slot? What happens? Does it execute? Does it not execute? Does it leave things in a weird state? Just don't do it. So that's about the easiest way to explain how you can use the delay slot. And so now we will use the delay slot because we can see... Oh, the other thing to note, the delay slot, now there's a little different variation, and we'll come to it. It's the branch likely instructions. Those are really nice, really cool, but we're going to cover those later. So this is the standard branch if not equal. And what we can do is we take... so the branch instruction does all of its background tasks. It does its comparison, it goes and gets the values from the registers, does the comparison, and it just before it actually goes and does this, goes to this label, is when it executes the delay slot. So this instruction that happens to be just before the branch can be moved here, and it is essentially in the same sequence because of how the branch instruction executes. So, and part of the thing here is that notice that the T1 register is actually used in the branch and in the add-I. So you want to be careful about this, and sorry, just thinking about the clearest way to explain this. So as I said, the compare of these two registers occurs, then the delay slot occurs, and then the jump or the branch to a label occurs. So they're kind of intermeshed, interwoven there, but it does work, and it does give you another instruction cycle to use, and it's a cool trick when you get to use it in things like this. So real quick, now that I did do that change, I am going to come back and make and debug. And F9 is my breakpoint, and there's my green line. So it actually didn't change any of the behaviors. Everything worked exactly like we saw the previous time, but we just moved this line of code and made the delay slot more useful. And that is a line. All right, so I'm gonna take just a couple of minute break, and we'll see if we can do a. I think we'll try a vertical line. There's just a little difference there. It's not too big of a deal, and maybe we'll get to a square or a rectangle. So hang with me. I'm gonna stop the video, probably continue the stream, and